Okay, so before the break, we have talked about the how to using the Fourier basic function to approximate a function, and so we have learned that if the function is a periodic function, then Fourier basic function is the best choice, right? And for the non-periodic function, we may not Fourier basic function may not be the best choice because Fourier basic functions is a periodic function. Therefore, for non-periodic function, we recommend to using splines basic functions. So spline basic functions are basically a polynomial function joined end to end. So these segments are constrained to be smooth at the joint. The joint points is called knots. So the spline basic function are defined by the order of the polynomial function. Order here is the degree plus 1, and also the location of the knots defining the system. So there's several types of spline basic functions. The most commonly used spline basic function we use are called B-spline basic functions. So fortunately, there's already software available for us to specify these basic functions automatically to satisfy these constraints. So we don't need to work on this B-spline basic function ourselves. I will show you later on how to using the FDA package in R to create these B-spline basic functions. Okay, so here this is one examples again for the temperature data. So basically here each vertical dashed line represents the location of one knot. Okay, so basically here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we have 13 knots. Okay, so then this 13 knots basically partition the whole time interval to 12 segments. So in each segment, we will have order m polynomial function. So here, this is the order 1 polynomial spline basic function. So in each segment is the order 1 polynomial, basically the degree 0 polynomial, basically the constant. Okay, so in each segment, basically it's a constant 1 function. So then we can create this. Then we can create the B-splines with the order 1 B-splines with this 13 spline knots. So then we created these basic functions. Then we can use these basic functions to approximate the Vancouver temperature curve. And you can see here, basically in each segment, basically is the average of the temperature in each intervals. Okay, so this is when we're using order 1 B-splines. So we can increase the order of the splines. We're using the same 13 splines knots. We're now using order 2 B-splines. So order 2 means in each segment is a degree 1 polynomial function, is a linear polynomial function. Okay, so you can see here for this order 2 B-splines, basically it's a linear function in each segment. Okay, and also this segment is continuous, is joined together at these knots, right? Okay, and also you can see here, so this is to show like a one basis function, order 2 B-spline basis function. And you can see here, this order 2 B-spline basis function is 90 at 2 segments, right? Okay, so this is a very important feature for the B-splines. So now we can using this order 2 B-spline basis functions to approximate the temperature curve, and you can see now this temperature curve become a continuous, right? A continuous function. Okay, and you can see here it is not smooth. There still will be a sharp change in the peak here, right? But it's continuous now. Okay, so now we can look at the order 3 B-splines. So this is one order 3 B-splines with this 13 knots. And you can see here, for this is the left panel to show one order 3 B-spline basis function. And you can see here, for this B-spline basis function, it is 90 at 3 segments. Right? And so the right panel is to show you the approximation on the temperature curve when we use order 3 B-splines. You can see here, now we have this blue fitted curve is a nice, continuous, smooth function, right? On the whole intervals. Okay? And we can try to look at order 4. So order 4 B-splines means in each segment, it is a degree 3 polynomial function. So basically, this is to show one order 4 B-spline basis function. And so this basis function is 90 at 4 segments, right? And we said in each segment, actually it's a one separate cubic polynomial function. Okay, so here they will choose this cubic polynomial function very carefully, such that this separate piecewise cubic polynomials is a continuous joint in these knots, and also the first derivative and the second derivative is continuous in these knots as well. Therefore, it looks like one polynomial function. Actually, here, this is a 1, 2, 3, 4. It's a 4 piecewise cubic polynomial function jointly smoothly together. Okay, so this is a one order 4 B-spline basis functions. Okay, and if we using this order 4 B-spline function is also called a cubic B-splines because in each segment is a cubic polynomial function. Okay, so cubic B-splines actually is also the most popular B-splines we use in practice. The reason is because cubic B-splines can guarantee that the second derivative is continuous. Okay, so this is the most popular B-spline we use in practice. Okay, so this is the right panel to show the fit when we're using the cubic B-spline. You can see here we already get a very smooth, continuous fit temperature curve. And we can increase the order of the B-splines. So here is the order 5 B-splines. So you can see this left panel again to show one order 5 B-spline basis functions. And you can see here this order 5 B-spline function is 90 at 1, 2, 3, 4, 5 at 5 segments, right? Okay, and here this order 4 B-spline basis functions actually is jointly by 5 order 5 polynomial function together in these knots. Okay, so this is order 4 B-spline basis functions, and we can do the fit. The fit is still pretty good, and we can increase the order. And you can see, surprisingly, the fit actually doesn't change too much, right? Okay, so this is a nice thing about the B-splines. So we find in practice that for B-splines, the most important thing is about the knots. Okay, we know the B-splines is defined by the order and also the location of the knots, right? And in practice, we find that the location of the B-splines actually play a more important role when we do the fit. So the order of the B-splines actually doesn't change the fit too much. Okay, so therefore, when we choose B-spline basic functions, we will choose the order to be cubic B-splines. Okay, and then we will try to select a different number of knots. Okay, so this is the main principle. Okay, because you can see here, even you using high order B-splines, the fit will not change too much. Okay, so this is one principle we use in B-splines. So we only using the higher order B-splines when we want to estimate the derivative. Okay, for example, if we only want to estimate the temperature curve itself, we will using cubic B-splines. We will using order 4 B-splines. If we want to estimate the derivative of the curve, we will increase the order by 1. So we will be using order 5 B-splines. Okay. Similarly, if we want to estimate the second derivative of the function, we will using order 6 B-splines. Okay. The reason is we want to make sure the second derivative of the estimated function to be continuous. Okay. Yeah. So this is basically the principle when we choosing the B-splines. So I didn't mention here is about the number of B-splines. So basically, the number of B-splines is equal to is fixed. Is equal to the order of the B-splines plus the number of interior knots. Okay. So for example, if we using cubic B-splines with 13 knots, how many basic functions will we have? Cubic B-spline with 13 knots. Boyi, do you know how many basic functions? 15. How do you get 15?
Order cubic. Cubic is order 3.
Yes.
4.
Cubic is order 4. Yes.
Order 4.
Yes.
17.
So
13 interior nodes.
Yes. So we have actually in our example we have 13 nodes. So 13 nodes means we have 11 interior nodes, right? Don't including the 2 boundaries. So for B-spline we have to define at least 2 nodes in the boundary. Okay. So there has to be a nodes, 1 node in the boundary. So for the 13 nodes we will have 11 interior nodes. So the cubic B-spline means order equal to 4. So 4 plus 11 is 15. So basically here for cubic B-splines, order 4 B-spline, we will have 15 basic functions. Okay, and so this is about the number of basic functions. So therefore, if you determine the order of the B-splines, you decide the number of interior nodes, then you will decide the number of basic functions. Okay, and so here so if the order of the B-splines to be m, then if you then use m order m B-splines, the derivative is up to m minus 2 continuous. Okay, and also I also mentioned that for B-spline basic function, they are positive over at most m adjacent intervals. Okay, so for example, if for cubic B-splines, they are be positive over at most 4 adjacent intervals, 4 segments. Okay, this is called compact support properties for B-splines. Okay, so this can enable us to do the fast computation, because you can imagine for one B-spline basic function, they are 0 in most time points. Okay, so they are only 0 at most m adjacent intervals. Okay. And also we have the constraints that the sum of all B-splines together is always equal to 1. Okay. So the most popular cubic splines is most popular B-spline basic function is order 4 B-spline basic functions. So so how do we choose as we said, the B-spline basic function are decided by the number of nodes and also the order of the polynomial functions. So generally, if we are interested in k derivative, we will define the order of the B-spline to be k plus 2. Okay. So for example, if you just interested in the curve itself, then the k equal to 0, right? So therefore, you will using at least k plus 2 will be 2, will be the linear B-splines. Yeah, I think generally we want generally to be k plus 4 here. So if we're interested in the curve itself, we will using cubic B-splines. Okay. If we want to using the first derivative, we will using order 5 B-splines. If we want to estimate the second derivative, we will using order 6 B-splines. So generally, we will put equally spaced nodes just to make our life simpler. In some special cases, when the number of observations are not equally spaced, we may want to put more nodes when we know the function has more curvature, and less nodes when the function has a small change. But we want to make sure that in each segment there will be at least one data point, okay, to make sure the B-spline basic function is identifiable. Okay, so later on we will discuss a very simple principle. So basically, we will put one node at each point of observations. Okay, and so in that case, for example, if we have 100 time point with observations, we will put 100 nodes. If we're using cubic B-splines, then the number of basic function will be 4 plus 98, so equal to 102 basic functions. In other words, we will using 102 basic functions to approximate these 100 data points. Definitely, we will have overfitting problems. Okay, so we will discuss how we can solve the overfitting problems when we place one node at each point of observations. There are also some useful, kind of more advanced techniques. Is that if you want to have some as we said, when we using B-splines, it will guarantee the continuous of the function. So in some cases, you may want to have the function to be discontinuous, or you want the derivative of the function to be discontinuous. In that case, you can do this by putting multiple nodes at the same location. Okay. So for example, if you're using cubic B-splines, so for cubic B-splines, the second derivative will be continuous, right? But if you put 2 nodes in the same location, in that case, that location, the second derivative will not become continuous. Okay, the second derivative will become discontinuous. If you put 3 nodes at the same location, then the first derivative will become discontinuous. If you put 4 nodes, then the function itself in that location will become discontinuous. Okay, so this is a kind of one technique. When you want to fit a function which is discontinuous, or the derivative is discontinuous at some locations, you can put multiple nodes in the same location. Okay. Yeah, so this is a kind of more advanced technique you can use. So there are also some other basic functions you can use, such as constant basic functions, power basic functions, exponential basic functions, and also there are some other basic functions, such as the wavelets. Okay, and also there's a popular empirical basic function called functional principal components. Okay, so we will learn how can we estimate these functional principal components later on when we learn this topic. Okay, so this is the basic functions. In summary, when we estimate the functions, so if the function is a periodic function, we will use the Fourier basic functions. Okay, if the function is non-periodic, then we will use the B-spline basic functions. Okay. Any questions? Yes.
I think in the real situation, if we just look at the data and then we cannot define whether it's periodic or non-periodic, then which we should use?
Let me see. So in reality,